Okay, hello students. Welcome back to General Chemistry 2 lecture. Today I'll be covering pH of salt solutions, and this also covers quiz 11 in the General Chemistry 2 sequence. So just a reminder about what a salt is that a salt right here, a salt is an ionic solid, and it contains a cation, a positive ion, other than hydrogen, and a negative anion, other than hydroxide. And when a salt dissolves in water, it's aqueous, and it can separate the anions, and the cations separate, and it can potentially affect the pH. It depends. And we can predict whether the pH is going to change, given a salt, whether it's acidic, basic, or neutral. And these four rules here are conceptual rules that can help us to decide that. But when applying them, it can be challenging. So what I have down here, I'll make a little dot here. What I have down here is really the concept of determining whether a salt is acidic, basic, or neutral. When you mix a strong acid and a strong base, you get a neutral salt. The strong and the strong cancel each other out. So you get a pH that is equal to 7. So it's neutral. When you have a weak acid plus a strong base, you get a basic salt. And basically the strong base is controlling the equilibrium here, and the weak acid is too weak to control the pH. So you're going to get a basic salt because the strong base is taking over. So you're going to get a pH that's greater than 7. And opposite, when you have a strong acid and a weak base, the weak base is too weak to control the pH, and the strong acid takes over. So you get a pH less than 7. Now, this may seem very easy in concept, but it can be a little bit more challenging when applying to an example. So let's do an example. I do have 3 example problems at the end, so this is not one of them. This is just a bonus problem. So let's say I have the compound, just thinking something off the top of my head. Sodium carbonate. So carbonate has a -2 charge, sodium has a +2. We're past that. So I want to know whether sodium carbonate is going to affect the pH of a solution, and I want to know whether this salt's acidic, basic, or neutral. And you're probably saying, I have no idea. Well, we have to work backwards when given these types of problems. How are we getting a carbonate, and how are we getting a sodium ion? So where is the base and the acid coming from? So this is where you need to learn your weak acids and your strong acids versus your weak bases and your strong bases. So I'm going to write the neutralization of sodium carbonate, which is basically where you just add a compound with water, which is what I'm going to do here. And when I do that, we'll see what happens. And I form my products, and I get HCO3 and sodium hydroxide. Well, wait a minute. Isn't this interesting? These two compounds should look very familiar. Change colors here. HCO3 is carbonic acid. And it's one of your weak acids. And this is sodium hydroxide. I can't fit that. But this is a strong base. So what does sodium carbonate come from? It comes from carbonic acid, which is a weak acid, and sodium hydroxide, which is a strong base. So which scenario do we have here? We have a weak acid and a strong base. So sodium carbonate is a basic salt. And that is how these problems can be approached. This is how this particular problem should be approached, but that's how you have to think about it. So it's not as easy as you might think just from this example here. This is how you got to think about it. Now, these are some more general rules, but like I said, I don't like to make rules. Rules are helpful, but they don't apply to everything. And when you make rules, then you're kind of putting yourself in a box to critical thinking, because not all critical thinking questions are going to apply to a rule. So if you box yourself in with rules, then you're not going to be able to apply what you're learning. So while these rules can be helpful when you're first learning it, don't put yourself constricted to this. So these are some general rules that you can reveal. Notice how I say in general. It's not set in stone, but in general, these are some things that you can review. Now, one more thing that I wanted to talk about that we should have talked about in our last lesson, but I forgot, is the dissociation of a polyprotic acid. Now, we only talked about monoprotic. I'm spelling this wrong. Monoprotic. And that means one hydrogen ion, or proton. Diprotic, well, I think you know where this is going, would mean two hydrogen ions, and we can go so on until we get polyprotic, which is many hydrogen ions. So in this case, we're given phosphoric acid, which is a weak acid, and it dissociates in 3 steps because it has 3 hydrogen ions. So it's actually going to have 3 ionization constants. For each step of the dissociation, getting rid of the hydrogen ions, we have a different Ka. And this is an important step, especially for pH of salt solutions. When we're looking at calculating the Kb, well, first we'll say when we're calculating the Kb, we want to use, I apologize. Whoops. Sorry about that. When we're calculating the Kb, we want to use the smallest Ka. And this obviously only applies to polyprotic acids because that's when you would have multiple Kas. So, and it would be the opposite for the Ka. So if you wanted to calculate the Ka, you want to use the smallest Kb. So if I wanted to calculate the Kb of phosphoric acid, I would use the smallest Ka. And in this case, it would be this one here, the 10 to the negative 13th. So that's an important thing to note here. Other than that, that's pretty much it when it comes to salt solutions. The math changes just slightly, and we'll talk about that right now. So let's get started. What is the pH of a 0.5 molar sodium acetate solution? So I'm going to write the dissociation of the weak acid. So you have sodium. So actually, I'm giving things away, but it's sodium acetate comes from a weak acid, acetate. So let's continue. I keep giving things away. Sorry about that. So here we have sodium acetate, and it has an equilibrium. And what we get is the sodium ion and the acetate anion. That's a 2. So this here is the only thing that could be contributing to our pH, and this is our conjugate base. So we know that sodium acetate is going to be a basic salt, because not only does it come from a weak acid, but we're forming a conjugate base in our dissociation, and this conjugate base is the only thing that's contributing to the pH because the sodium is not. So when we're going to want to calculate the pH, we're going to want to look at this dissociation here. So we're going to take this a step further and write the dissociation of the conjugate base, the acetate ion, C2H3O2 minus. And we're going to dissociate this in water because it's a weak base, remember. even though it's a conjugate base, you still have to dissociate it in water. And we're going to get back acetic acid. Oh, whoops. Keep doing that. We're going to get back acetic acid. And we're going to get that hydroxide that's contributing to our pH. So now, after we've solved the dilemma of what kind of salt this is, we can start our math. So that's what's the different here. You got to figure out what's contributing to the pH, and then you take it a step further, and then you can start your math. So I'm going to make my my ice table. I think you guys like the ice table more than the IRE table, so I'll do the ice table. So initially, what do I have? I have 0.5 molar of my conjugate base. I have 0 of my products. You don't have to worry about water. And I'm going to lose X on my product side, but gain it on my reactant side. So very typical kind of scenario here. So at equilibrium, my conjugate base is going to have 0.5 minus X, and I'm going to have X and X on my product side. So since this is a weak base here, I need to make my Kb expression. And that would equal my acetic acid I got that mixed up. Sorry. That's going to equal my acetic acid concentration times my hydroxide ion concentration, and that's going to be divided by my conjugate base, which is the acetate anion. So, what is my Kb? Well, I'm given the Ka. I didn't give you the Kb. Well, not a huge deal. We can just find the K. We can find the Ka. Ka is going to equal, the Kb is going to equal the Kw divided by the Ka. So that's going to equal 1 times 10 to the negative 14th divided by the Ka, which is 1.8 times 10 to the negative 5th. So we get our Kb to be 5.5 times 10 to the negative 10th, and now algebraically this equals 8x squared over 0.5 minus x. But since the Kb is less than 10 to the negative third, we can drop the x. So we're going to solve for x here. Just cross multiply and take the square root. So we get x to equal 1.67 times 10 to the negative 5th molar. But be careful here. This is not our hydrogen ion concentration because it's our weak base dissociation. It's our hydroxide ion concentration. So we can get our pOH by taking the negative log of this value, and we get our pOH to be 4.8, which means our pH is equal to 9.2. And that makes sense because we said it's a basic salt, so the pH would be greater than 7, so 9.2. In our next example, we're asked to calculate the pH of a 0.2 molar sodium carbonate solution, and I've given you the 2 Kas because it's a this acid dissociates twice because it's diprotic. So let's begin. Whoops. So I'm going to write my dissociation of my salt to determine what's really going on, what's contributing to my pH, and I get my sodium plus carbonate. So the carbonates coming from the carbonic acid, I kind of gave that away to you by giving you the Kas. That's coming from the carbonic acid, which is a weak acid. But the sodium's coming from the sodium hydroxide, which is a strong base. So strong base, weak acid, we get a basic salt. So what's affecting the pH here is this carbonate ion. So that's what we need to take a look at in our dissociation here in our next step. I'm just going to erase this for more room. So we're going to write the dissociation of the conjugate base, which is the carbonate ion, and we're going to add water to it. And since it's a conjugate base, we have to add water and include the equilibrium symbol, and we're going to get back the acid, but remember we're missing one proton, so we're going to be careful with our Kas, plus the hydroxide. Now, since this is a dissociation of a polyprotic acid, like I said earlier, we're going to use the smaller Ka. So we're going to use this Ka in our calculations. So initially, what do I have? I have 0.2 molar, and I have 0 of my products. My concentrations that I'm going to react, I'm going to lose X, but gain it on my product side. And at equilibrium, I'm going to have 0.2 minus X, and then plus X and X. So because I'm looking at this hydroxide ion concentration to get my pH, I need to make a Kb expression. And the Kb expression would equal, algebraically, X squared over 0.2 minus X. But we need to find the Kb, and the Kb would equal the Kw divided by the second Ka, Ka2, because we use the smaller one. So the Kb is going to equal 2.1 times 10 to the negative fourth, and that's going to equal X squared over 0.2. And we can drop the X here because the Kb is less than 10 to the negative third, so we'll drop the X. So when you solve for X, you get, this is actually a hydroxide ion concentration, but we get X to be 6.5 times 10 to the negative third molar. So by now you should be able to get the pOH from this, and the pOH would be 2.19, and the pH would be 11.8, let's see here, 11.81. And that makes sense because, like we said in the beginning, it's a basic salt. So we get a basic solution. So just got to be careful here with your Kas. And once again, it's all about identifying what's contributing to the pH. And in this case, it was the carbonate ion. And finally, we're asked to consider aqueous solutions as each of the following salts, and we want to determine whether they're each acidic, basic, or neutral. So basically, we're going to be doing what we did for the first part of each problem for each of these. So if we're looking at ammonium iodide, what is this coming from? Well, it must be coming from an acid, and the only acid with iodide is hydroiodic acid, and it's going to come from the weak base ammonia. So ammonia is a weak base, and hydroiodic acid is a strong acid. So strong acid, weak base, we get an acidic salt. B, we're getting, oh, I'm glad I put this on here, zinc nitrate. Also, by the way, in all of these, since it's neutralization, we're getting water as a product. but I'm not going to write that each time. So zinc nitrate, what's that coming from? Well, it's got to come from nitric acid, right, because that's where that nitrate's coming from, and zinc hydroxide. Now, zinc hydroxide is an interesting exception to the strong base rule. It is one of the only hydroxide that's a weak base, and nitric acid is a strong acid. So I forgot to put this on our last list, so just remember zinc hydroxide is a weak base. So once again here we're going to get a acidic salt. Okay. C, we're asked about, let's see here, potassium chlorate. So that must be coming from the perchloric acid, because that's where we're getting our hydrogen ion from, and that's a strong acid. And it's also going to be coming from potassium hydroxide, which is from a strong base. So a strong acid and a strong base yield a neutral salt. And finally, we're asked about sodium phosphate. This one should be pretty clear. It's going to be coming from phosphoric acid. Once you do a lot of these, you know, it comes easy to you. And sodium hydroxide. So the phosphoric acid is weak acid, and the sodium hydroxide is a strong base. So a strong base and a weak acid, we're going to get a basic salt. And this is the pH of salt solutions.